Okay, I think we can start now. Okay, so let me know if you cannot hear me lah. So I think you can hear me, right? So okay, let's start. So we will look at the first question. The first question is we have a particle of mass 2m kg, okay, traveling 3 meters per second, collides with another particle mass m, and it is traveling at the same direction. The velocity is 2 meters per second. So after the collision, so the first particle continued in the same direction, but the velocity now becomes 0.5 meters per second. So we need to find the velocity of the second particle. So for this question where it involves a collision, so we know we are going to use the momentum. So the conservation of momentum tells us that we have m1u1 plus m2u2 is equal to m1v1 plus m2v2. So basically it is not difficult to do it. So how are the marks awarded in this case is that we have the first mark, okay, is given when we see any momentum term is correct. So either one of your m1u1, m2u2, m1v1 or m2v2, just if any one of that is correct, you substituted the correct value, then you get this first mark. And then the second one is when we actually have all the terms substituted correctly. Okay, and the last mark is we actually find out what is the value for the v, okay, of the second particle. By getting the correct answer, we will actually get the last mark from there. Okay, so I guess for the first question, it is not difficult to do. Okay, so we can actually look at the next question. So for the next question, okay, what we have in this situation is that we have got a mass, okay, of 2 kg. So this is a smooth horizontal floor, and then these three forces act simultaneously on this mass, okay, and it starts to move. So what happened to this figure here is that this is actually the figure that is viewed from the top. Okay, so this is actually a top view, and we actually like try to pull this object of this mass from different direction. Okay, so what is the solution, okay, or the approach given by the mark scheme is that, so the mark scheme assumes that we have got the resultant force because it says it starts moving. So if it is in equilibrium, so it will just be there at rest. But this one, this object actually starts moving, so we know that it is not in equilibrium. So it will actually have a resultant force. Okay, so for this resultant force, okay, what we have is for this mark scheme, they assume that the resultant force is in this direction, as we can see from here, and then this resultant force will have the angle theta to the north. So why can we say something like this? So why do we know like the resultant is there? Is because if you actually look at the magnitude of the forces in a direction, so we have a 3 Newton force to the left, to the right, and then we also have another 5 Newton up. So if we actually look at these two forces, the 5 Newton and the 3 Newton, as compared to the 1.5 Newton in this direction, so because the 5 and the 3, it looks like, okay, the two forces are greater than the force which is like 1.5 Newton. So we actually expect that the mass will actually move, okay, somehow in the direction which is in the first quadrant. Okay, so this is what is provided in the mark scheme. So we will see like other similar ways to work on it later. So how do we do that is we'll assume that we have the magnitude r, okay, and the direction is given by the theta, okay, which is theta degree to the north. So the components, okay, for this resultant force is that for the vertical component, so this means the vertical component. So the vertical component here is given by r cos theta, because we have got the theta. Okay, we have got the theta which is to the north. So r cos theta gives us the vertical component of this resultant force. So how do we consider this one is by looking at, is there any other vertical forces which make this resultant force which is in the vertical direction. So in the vertical direction, we have got 5 Newton which is going up, okay, which is shown here, and then another one we have this 1.5 Newton, we need to resolve it down. Okay, so when we resolve this 1.5 Newton, we will actually have 1.5 cos 45 degree. So that gives us the r cos theta is given by 3.9393. So this is the first thing that we can actually find. So that will be the vertical component of our resultant force. So this is by assuming that we do not know about we do not know about the R. So what happens is that usually, okay, in the class, what happen usually is that we will just assume that for this direction is a positive x, this direction is a positive y. So we are actually trying to look at the resultant of the x direction and for the y direction. So this one we're actually looking at the resultant of the y direction. So the resultant of the y direction is assuming going upward is positive. So we have 5 which is going upward, and the force which is going downward is of course about 1.5 cos 45. Okay, so basically this value is exactly the same as what we have here, lor. So our r cos theta is basically our resultant force in the vertical direction. Okay, the vertical component of the resultant force. So similarly, okay, what we do to this horizontal component to this resultant force is that, so the horizontal component for this resultant force is we have got r sine theta. Okay, r sine theta is our vertical component. So just look at all the the horizontal forces that we actually have in this case. So for the vertical forces, we have got 3 Newton. To the right, we assume that it's a positive, and to the left, we need to resolve this 1.5 Newton. So to resolve this 1.5 Newton, we get 1.5 sine theta. Okay, so we get 1.5 sine 45 is to the left. So by considering the net effect, the r sine theta is 1.9393. Okay, so this is actually the horizontal component of our resultant force. So how do we actually get this resultant? Okay, the resultant here is that because just now we have found two things. Okay, we have found two values. So the two values will be our rx and the ry. Okay, so we know that this is the resultant. Okay, so how do we find the resultant is by using this triangle. So for this triangle, we will have, this is ry. So this is we can actually use the Pythagoras theorem to help us to find the r. So we just have to square the rx and we square the ry, and we take the root of the sum of that two. So we can get the r, which is the magnitude of the r is 4.39 Newton. Okay, so far we have already got 3 marks. So 1 mark for looking at to find the vertical component of the resultant, another mark for the horizontal component. The mark here is to find the resultant, okay, the r. So after that, how do we actually find this theta? So to find this theta, what we have is if we actually follow the figure that we have earlier, we are supposed to find this theta. Okay, and then if we are actually using this triangle, so this theta is the same as the theta here. Okay, so if we use a tangent theta in this case, so the tangent theta here is given by rx divided by ry. Okay, so by using this, we actually get the tangent theta is equals to 0.4923. So with that 0.4923, we can actually solve for the theta in that case. So the theta is 26.2. Okay, so in that case, we know that the resultant, okay, is going in this direction, okay, where we have already circled earlier on. So this is our resultant. Okay, so we know that the net force, okay, which is the resultant, okay, is equal to our ma, okay, by using the Newton's law. So we know that for this object, the mass is 2. Okay, so we have got the net force, okay, which is our resultant force is equal to 2 times a. So in that case, you can actually find out what is the value for the acceleration. So in this case, the acceleration is 2.20. So we'll actually get another mark for that. So how do we actually obtain the last mark is that we must specify, okay, we must state clearly what is the direction of this resultant force. So we can say that this resultant force is at the bearing of 26.2 degree, or you can use any other equivalent description to it. Okay, so as long as you can state this direction clearly by referring to the north, to the east, or positive, negative x-axis, things like that, then you actually get the last mark from here. Okay, so this is the question that we have for the second one. Okay, so I think we can actually look at the third question here. The third question is the general motion on a straight line. So for this question we have, okay, at time t is equal to 0, the particle p is 10 meter from point O. So okay, usually what happens is we actually look at the questions carefully. So in this case, initially when time is equal to 0, the p is already 10 meter from the point O. If we make the point O as the s is equal to 0, okay, so usually we refer the point O as the displacement 0, okay, but here the particle p is already at 10 meter away from the point O when we have the t is equal to 0. So the particle p, okay, does not start at O. Okay, so this is a thing that we need to be careful. And then, okay, what it says is it is moving in a straight line at a velocity of 2 meters per second away from O. Okay, so for the first 10 seconds, the acceleration of p is given by this expression, okay, 5 minus 1.2 t squared. So first is to find the distance of p from point O at time t is equal to 6 seconds. Okay, so we actually have to find this one first. So we need to find the distance of p from point O. So basically is to find the displacement. Okay, so before we can find the displacement, we need to find the velocity first. So for the velocity, we know that it is going to be integrate a with respect to t. So we have got the expression for the a already here. So integrating the a will give us this expression. Okay, 5t minus 0.4 t cubed plus a c. So for this one mark is given for the correct integral result. Okay, whether or not we actually include the c. Okay, so as long as we get this correctly with or without c, then we'll get the first mark. So of course, it's very important for us to actually find what is the value for the c from there. So the value of the c is obtained by using t equals to 0, the v is equal to 2. Okay, because it is already said that it starts with this velocity. Okay, the v is equal to 2 in the beginning. So we can actually find the c from there. The c is a 2. Okay, so by doing this, we will get another mark from there. Okay, so next one, because what we actually wanted to find in this case is we want to find the distance. So for the distance, we have to integrate the v log. Okay, with respect to t in this case. So for that one, it's pretty easy to integrate in this case. So as long as we integrated all the terms correctly, okay, in this case, we will actually get the marks for that. And the next mark is only given when we actually find out the correct value for the constant in this case. So for this constant, we use k instead of the c lah. Just trying to use like different constant to not to confuse ourselves. Okay, so we know that when t is equal to 0, the s is equal to 10. Okay, this is what we have checked or seen earlier. So our k here is a 10. So getting this correct value of the constant, we get a 10. We get 10 and we get a mark from there. Okay, so after that, we actually get the correct expression for the displacement. Okay, so the displacement is given by this expression, and we are supposed to find when time is equal to t equals to 6 seconds. So what is the distance from point O? So we just have to substitute this t, okay, into the displacement, the s. So when we actually try to substitute that in, right, we get negative 17.6 meter. So just have to be careful that the question actually asks for the distance, okay, not the displacement. So when we actually give our answer, the answer should be in a positive value. So it should be 17.6 meter as the distance. Okay, so we have to really state out loud that is the distance. And the last part of the question, it says state whether it is moving toward or away from O at that time. So how do we actually check that is we will actually have to find out what is the velocity of this particle, okay, when we have t is equals to 6. So how do we check that is we actually substitute t is equals to 6, okay, into the velocity. So when we calculate, we get negative 54.4 meter per second. So in this case, it is moving away from the O. Okay, so what happened to this situation is that, okay, we have got this is our point O. Okay, and when t is equal to 6, our point P is here. Our particle P is here because this is a positive direction, this is the negative direction. Okay, so S is equal to negative 17.6 means the P at that time is at the left of our O, and the negative of the V indicates that it is moving in the negative direction. So it is actually moving like this, okay, in the negative direction. So it means it is actually moving away from O when we have the T is equal to 6, okay, at that instance. So with that, okay, how are the marks awarded is that we have the 1 mark is given when we say it is 17.6 meter away from O. You need to state this as something like a distance, okay, without the negative sign. And then another mark is given when you say it is away, okay, from the O. So this mark is only given when it is seen that you try to evaluate your V, okay, and you get a negative value for the V. So so this is the only way that we can tell whether the particle is moving away or moving towards the O. Okay, you must calculate this V. Then only you get this by stating, okay, it is moving away from the O. Okay, so this is for the third question. Alright, for the next one. So two particles of different masses, we have got 0.1 kg and 0.2 kg are attached to the ends of a light inextensible string, okay, which passes over a smooth pack. So this is basically like a pulley question. So first, given that particles move freely after they release from rest, so use an energy method to calculate their common speed after each has traveled 0.6 meter. So for this one, they actually specify we can only use the energy equation to actually calculate this. So we are not supposed to use the usual Newton's law to actually calculate this one. Okay, so when we actually ask about this energy, so we will actually use the work energy equation. So the most common version that we use is that the change in KE is plus change in PE is equals to the total work done. Okay, but for this case, if you actually look at the situation, there is no work done here. Work done is when we have the case that we are trying to pull that object, or it actually undergo a certain resistance, things like that. So in that case, there is no work done involved here. So for this one, okay, the change in KE plus change in PE is equals to 0. So in another word, what happened for this one is that the gain in KE, because why do we use the gain in KE is because the system starts from rest, okay, the two particles are initially at rest, and then if they start to move when they are released, they start to move, so they have a certain velocity, so there will be a gain in the KE. So this gain in the KE, okay, is actually equals to the loss in the PE. Okay, if you actually look at this one, so if KE gains, the PE will actually lose. Okay, in order for this equation to be a 0, so we need to find out for each one. Okay, so in that case, the gain in KE is we know that the KE is half mv squared, so we just have to find out the gain in KE for both particles. So in this case, take note that for both particles, they are moving at the same velocity. Okay, so this is a pulley system, so it is impossible for them to move in different velocity because they are connected by a string. Okay, so they cannot move with different velocity. So they will have the same velocity, which is the v in this case. Okay, just have to add up the KE for both particles then we will get this expression, okay, 0.15 V squared joule. So anything which is similar to this one, this is seen, okay, then we will get 1 mark from there. Okay, so we will look. So now we will look at the loss in the KE. Sorry, the loss in the PE. So what happened to the loss in the PE is that we have got we actually have two particles, okay, and each of that they actually have some loss in the KE. So what happens is that we have got two particles, okay, one is 0.1 and another one is a 0.2. So when this system is released, we will actually expect the 0.2, okay, the particle with a 0.2 kg will actually go down, so that is a loss, okay, in PE. For 0.1 we will actually go up, there will be a gain in a PE. So the net loss in a PE is by using the PE for the 0.2 kg, which it has already lost, to minus with the gain in the PE of the 0.1 kg particle, okay. So the situation is like this. So for 0.1 kg, it will actually go up. So this is a gain in PE, okay. For 0.2, it will actually go down. So this is a loss in PE. So now we are looking at the loss in the PE. Okay, so this loss in the PE will take the positive sign off. Okay, and this gain in the PE here will take the negative sign off. Okay, so because at last we will actually have a net loss in the PE. Okay, so by finding the MGH for both, we will actually have 0.6 by substituting their mass, the G, and then also the change in the height, because they both they have already moved for 0.6 meter. Okay, so by finding out this value, we have got 0.6, which is their loss in PE. So the next one is to consider the conservation of the energy, because they have got the gain in the KE is equals to the loss in the PE. Okay, because one gain, another one must loss. So we just equate them together, okay, for both of that, and then just trying to solve the V from there. So in that case, the V that we get is 2 meters per second. So with this, we can actually get another mark from there. Okay, so this is when we actually consider by using the energy equation. So next one, calculate the work done on the lighter particle by the string and use this to find the tension in the string. So what happens is that for this lighter particle, so it has gain in KE, and it also has the gain in the PE, because again, if this is the 0.1 kg, right, it will actually go up by 0.6 meter. Okay, and then at the same time here, the initial velocity is equals to 0, and then it has gained a certain velocity, which is like the V is equals to 2 in this case. So for this particle, it has got the gain in the KE, and then also the gain in the PE. Okay, so the gain and the gain in the KE, which is change in KE plus the change in PE, is equals to the work done in this case. Okay, so why we don't consider the work done in the previous case is because it is equals to 0. Okay, because we are looking at one side of the particle, okay, transfer the energy to another the particle, so they actually have a balance, okay, like that. So for this one, we are only looking at a certain part of the system, which we only look at the lighter particle. Okay, so it has a work done. So or in another word, why is this lighter particle can go up is because the string has already done some work to actually try to pull it up. Okay, so this is why we have got the work done by the string. So we just have to consider the KE and the PE of that lighter particle, which is the particle that has the mass 0.1. So the first mark is given by when you actually try to say, okay, there is a PE, there is a KE, so that's the first mark, and then after that we just substitute the values inside the expression, and at last we get the work done by the string is 0.8 joule. Okay, so for the following part, we know that the work done is given by F times S. Okay, so in this case, we can actually find out the tension by using the work done. So this is the work done W, and then T is the tension force, and then the S we know. The S is they already travel for 0.6 meter. Okay, so we can actually calculate the tension from this W is equal to Fs equation. So that will be 4/3n, or if you want to use the decimal, it will be 1.33 Newton, which is rounded off to 3SF. So for this, you'll get another mark from there. Okay, so we will actually look at the next question, which is question 5. So a car of mass 700 kg descends a straight hill, okay, which is inclined at the angle of 3 degree, okay, to the horizontal. So for this car, it will actually pass through the P and Q, okay, with different speeds given. And then they already tells us that, okay, the distance of PQ is 500 meter. So assume there is no resistance to the motion. So calculate the work done by the car engine from the P to Q. So the first thing that we know is this car is actually going down the hill. So what we have in this case is that we do not have any resistance in this case. Okay, so there is nothing about resistance mentioned here. So we can always use the change in KE plus the change in PE is equals to the work done. So in this case, the work done is by the car engine. Okay, so we just have to find out what happened to those KE and the PE. So for the loss in the PE is we have got mgh. Okay, so we know what is the M, what is the G, but for the H is we have to resolve a little bit because we have got 500 as the hypotenuse. This is the hypotenuse. Okay, we need to find out what is the height here. Okay, we know that the angle here is a 3 degree. So we have to use a sine, okay, to help us to find the height in this case. So the height is given by 500 sine 3 degree. Alright, so that will be our change in the PE. So the change in the PE is this 183,176 joule. Okay, so another one is a change in the KE. So the change in the KE there is we have to use the final minus initial velocity, their squares. Okay, so we use half m v squared minus u squared. Okay, so because it is already given for both velocities, so we can actually find out the KE, the gain in KE, and in that case. So for PE and KE, we will have 1 mark each. Okay, so finally, the work done by the engine is change in KE plus the change in the PE. So the change in KE is positive in this case because it is getting faster. Okay, so it has actually gained some energy. And then for the change in PE, in this case, this is our change in PE. The change in PE here is a negative because the car has gone lower. Okay, so it should be a decrease in the PE. So the change in PE here is a negative. So if we actually consider the work energy principle, so the work done by the car here is given by this number. Okay, so you can round off to 81.4 kilojoule, or if you don't want to use a kilo, you can use 81400 joule, which is also rounded to 3SF. So any answer which is equivalent to this, we will get another mark from there. Alright, so we can look at the next part. Assuming that, okay, further, the driving force produced by the car engine is constant. So calculate the power of the car's engine at P and at the midpoint of the PQ. So we have two parts to solve. So one is at the P. Okay, so because in the previous part we already find the work done by the car engine. Okay, so for this one we know that the work done by the car engine is actually the driving force times the distance that it has already traveled. Okay, so by using this, okay, we can actually get 1 mark by quoting this. We know that the driving force times the distance is equals to the work done, okay, by the engine. So the driving force here is this figure. So we can actually get another mark for the correct answer for this driving force. And then we know what is the velocity, okay, of this car at the point P. So the velocity is a 12. So to get the power, we can use the driving force times the velocity. Okay, so substituting the correct values, okay, in this dV will give us 1 mark, and then the final answer will give us another mark from there. Okay, so for this one, if you want to round to 3SF, you can also use 1950 watts, which is rounded to 3SF. Okay, so that is for the first part where we calculate the power of the car engine at a P. So what about for the midpoint of the PQ? So midpoint of the PQ, it means the car has already traveled for 250 meters from P. Okay, so this is the distance that the car has already traveled. So for that, okay, let's say, okay, we let the speed, okay, of the car at that midpoint, okay, to be W. So again, what we consider is that we consider the work done by the engine. Okay, the work done by the engine is equal to the change in KE plus the change in PE. Okay, so the work done by the engine is, we know this value, okay, from the previous one, because this is a driving force, okay, of the engine, because the question already mentioned that the driving force of this engine is constant, so it won't change all the time. And then this is a distance, okay, so this is the driving force times the distance, which gives us the work done. Okay, and for the PE and the KE, right, the PE will actually have mgh. So what happened here is we have got the m is 700, g is 10, the h is 250 sine 3. So this is the same idea like just now. Okay, it has gone downhill by 250 meter, and then the steepness is at the 3 degrees. So we have to use the sine to find the height. So this is the height, the change in the height. Okay, so the gain in the KE, so in this case is half times m times v squared minus u squared. We know that at P, okay, this is the velocity at P, and then at the midpoint we already said that, okay, let that speed to be W. Okay, so basically after that is a bunch of calculation. We will get the velocity at that point is 22.85. Okay, so after that the power we already know is to use the driving force times the velocity. So we already know the driving force, and we also know the velocity, which we have just calculated. So giving the final answer correctly, okay, we will actually get the answer mark from there. Okay, so that will be for this question. Okay, next one. So initially a box of mass m, okay, is at point O. Okay, is on a rough plane, okay, inclined at 15 degrees to the horizontal. So this block is projected, okay, directly up the plane along the line of the greatest incline with an initial speed of 4 meters per second. So it has an initial velocity, okay, and the coefficient of the friction is 1/10. So at A, okay, the box comes to instantaneously rest. So you can imagine what happens is that, okay, at point O, okay, the box is still moving with a velocity, or in this case they say the speed of 4 meters per second. So and then when it reaches the A, the box will actually stop for a moment before it will actually slide down again. Okay, so we're actually considering the first part of this motion first, until the point A where it stops for a while. Okay, so basically for this one is by using the forces, okay, the Newton's law, for us to actually solve this. So what happened for this one is we have got the initial velocity is a 4. Okay, this is the thing that we know, and then we also have the reaction force, okay, because it's on the surface, and we have got the mg. So the mass in this case is a capital M. Okay, they never give us what is the mass in this case, so it's a capital M. And then we also have the friction, okay, because it is already given the mu, the coefficient of the friction. So we just have to find out what is the acceleration in this case, because the box is moving up, so the direction of the acceleration will be also here. Okay, so before we can actually find out what is the A in that case, okay, we actually have to use F is equals to ma lor. So F equals to ma depends on our net force. Okay, so we will see what are our net force. So to construct our net force, we have got the reaction force. So the reaction force, the R is the same as mg cos 15, where we resolve the mg to the opposite direction of the R. Okay, so this is our R. And then this one is actually to help us to find the frictional force. So the frictional force is given by mu R. Okay, so finding this expression correctly, we will get 1 mark for that, okay, for the friction. So next is by consider F is equals to ma already. So the net force, okay, the net force is given by, we have got two forces. One is for the friction, okay, and then another one is for the mg resolved in this direction. So there will be mg sine 15. Okay, so our F is equals to ma. Okay, so our M is capital M, and then we have got the ma in this case. So the M that we have, okay, in this expression will be cancelled off with all the other net force. So because the net force is given by this one. Okay, so the net force, they will actually both take negative, is because our A is going up. So you can see that the forces which we have, the friction and then also the mg sine 15, if they are both going down, so they both should take the negative value. Okay, so once these two net forces, these two forces are seen, okay, we will get 1 mark from there. And after that, it's just calculate the value for the acceleration. So the acceleration here is negative 3.554. So 1 mark for this final answer. And eventually this box will stop, okay, at a point A. So we are supposed to find out how far it has already traveled. So we have to use the motion equation. So we can use v squared equals to u squared plus 2as. So in this case, we just have to find out what is the s in this case. So substituting the correct values into the v squared is equal to u squared plus as, we get 1 mark. And then another mark is to get the correct value for our distance of the OA, okay, which it has already traveled for 2.25 meter from there. Okay, so next one, find the speed of the box, okay, as it passes through O when moving back down the plane. So now the box will actually move down the plane already. So it is good for us to always label what we have for the A. Okay, so for this one, okay, the frictional force is still the same. We have got mu R, so the mu R remains unchanged. Okay, so now it's time for us to actually find out the net force in this case. So the net force is, we have mg resolved down the slope, which is mg sine 15 to minus the frictional force. So this expression is our net force. So the correct expression for our net force will get 1 mark from there. Okay, and now we just consider the F is equals to ma. So the M here is the capital M, and later on we actually cancel off all the capital M's. So we just have to find out the A from there. So the A here is 1.622 meter per second squared. So we get another method mark from there. So we already know, okay, from A to O, the distance that it travels is 2.25 meter. All right. So with that, okay, we are supposed to find out what is the velocity, okay, at the point O. So just use the same equation again, v squared equals to u squared plus 2as again, to find out, okay, what is the velocity. So we will get the another mark from there. So the mark before this is by substituting the values of the A and the S correctly. Okay. So that would be the second last question. So the last question that we will see. Okay, so this is rather a long question, but I will actually look at that carefully. So it's basically about the motion. Okay, so it involves two persons. First we have John. He actually has two stages of the motion. So you can see that for the first stage, he is traveling at the constant speed of v. Okay, and when it reaches the time which is 540 second, okay, he will actually slows down already. So with a deceleration, so he will actually do this for 120 second, okay, until it actually comes to a complete stop at the point B. Okay, and also for another person, okay, so Mary should actually starts at t is equal to 60 second. Okay, so what she do is you actually have she actually travel, okay, like this. So with acceleration followed by a constant speed, so it is already true that the constant speed is 4, and the deceleration, okay, before coming to a complete stop. Say they are actually moving towards each other, okay, for the John and Mary, if you actually look at the questions carefully. So John reaches B at the same time as Mary reaches A. So they actually stops, okay, at the same time. So for this, we actually look at the sketch of this axis. So this is what happened to the motion also for first. So this the graph in the upper part one here is for the John, because from A to B it is considered as a positive. So the V for the John will be positive all the time. Okay, so because John starts with the velocity, okay, which is called the V, we do not know what is the value yet. So he actually do this for this amount of time, okay, 540 a second, and then at last he will actually go deceleration. So deceleration means the this V will actually goes down lah. Okay, because he will actually get slower and slower until the V is a 0. Okay, so this is a graph for John. So for the first part of the graph, okay, we'll actually have 1 mark for the first part of the graph. Okay, so for the second one, for the graph for the Mary, so Mary starts from V is equal to 0, and it is at t is equal to 60 second, and then Mary will actually speed up. Okay, you see that there is a constant acceleration in the first part for the for Mary. So Mary is moving in a constant acceleration, but in this case everything it becomes negative already because she is moving in opposite direction. So when she's moving in the opposite direction, the speed of course is increasing from 0 to 4. Okay, but when we actually talk about the velocity, the values will actually go from 0 to -4 because she is traveling in another direction, which is in the negative direction. So the V will become more and more negative to indicate that she is actually speeding. Okay, but just the value of the V is become more and more negative. So this is why we have got the first part of the graph here, which is like going down here. Okay, so after that she will actually remain at the constant velocity. So of course the curve is a flat one. So after that she will actually decelerate. So decelerate means she's getting slower and slower. So the V will actually becomes smaller and smaller. Okay, we will actually the V will actually become a 0. Okay, so in that case the Mary actually reaches the A already at that point. Okay, so this would be the graph for Mary. So for Mary, the graph, okay, the second part, the second mark here is given when we have got the shape. So once you see going down, flat going up, you get 1 mark. Another mark is given when you actually label all the things, all the values correctly. Okay, so this is what happened to the graph. Okay. Next one, okay, find the value of V. So for this one, when we actually sketch the VT graph, okay, we one of the useful thing to know is it is very useful to see like what is the total distance that they have already traveled. So from the question, it is already told that okay, the distance of AB is a 2 kilometer. So 2 kilometer means 2,000 meter. So at the same time, what does that mean is the area under the curve for this one, okay, it should be 2000. Okay, and then it is not difficult for us to find the total area under the graph. Okay, so the total area under the graph is, for the first part, it consists of the rectangle in the first part. The second part is the triangle. Okay, so it shouldn't be very difficult to find out the area of the curve in this case. So this is equal to 2000. So once we have write out something like this, we will get the first one. And then basically after that, it's just solving for the V lah. So solving for the V, getting the correct answer, we will get 10 over 3, which is 3.33. So we will get another mark for the correct answer. Okay, so that would be for part 2. Part 3, find the time spent by Mary accelerating. So for this one, okay, if you actually look at the situation again, so in the question it says, okay, let me just erase this first. So in the question it says that this for Mary, the time spent on accelerating and decelerating are the same. So what we can see from the graph is that this part, okay, should be the same as this time. Okay, so we can actually give it a name. Say we have the time t is the time spent at the constant speed, which is 4 meters per second. So let's call this time period as a t. Okay, and then because Mary has already traveled the same distance as John, so the total area under the curve, which is this part, okay, should be 2000 as well. So we can actually find out what is the area, okay, of this curve. So how do we find this area? Is that, okay, we have got this one is a t, right? Okay, and then this one is a 600. Okay, and then this one is a 4. So basically we can actually use the area of a trapezium. So the area of the trapezium is, we have got 600 plus t, okay, we sum up the up and down, and then times the height, okay, which is 4 in this case, and then we times by half. So this is by using the formula for the trapezium. So in this case we can actually find out what is the t. Okay, so the t that we have is 400. So for this one, we know that for this period is a 400 second. So it is very easy for us to find out how many, what is the time that she spent in accelerating or decelerating. They are just the same. So it is very clear that, so this one is 100, this one is 100. So she actually spent 100 seconds in accelerating or decelerating. Okay, so how are the marks awarded is graph, as long as we see that you say the area is 2000, okay, or the distance traveled is 2000 or whatsoever, there's 1 mark for that. Another mark is to solve for the t, and then another one is to give the correct answer. Okay, so for this case, you in the mark scheme we actually use the t as the time spent for the constant velocity. You can also make this time where she spent for the accelerating or decelerating as t. So you should get the similar answer as well. Okay, so you actually get the answer no matter how. Okay, so the last question here is John passes Mary when both were traveling at a constant speed. So find the distance from A when John passes